The model file is 160 gigabytes. The graphics card has 8, and it still answers at half a token a second on a card that costs $200 used. That works because of one detail in how this tool is built. The model never fully exists in memory. One layer loads, runs, gets thrown away, and the next one comes off the drive. So here's the whole video. What oLLM actually does, the one job where it is the only tool that works, and then the 3 places where the trick stops working. The model is Qwen 3 Next, 80 billion parameters. Anwar Sharapudinov shipped it in September 2025 out of a hackathon in Astana, Kazakhstan. He had 8 gigabytes of video memory, 16 gigabytes of RAM, a pile of customer conversations he could not send to the cloud, and no inference engine that would load the model he wanted to use. The project is on GitHub, 2,700 stars, MIT licensed. The table in the README is 80 billion parameters, 160 gigabytes of weight, 50,000 tokens of context, 7.5 gigabytes of video memory, 180 gigabytes of disk. Hold that next to a standard local AI setup for a second. An 8 billion parameter model at 4-bit in llama.cpp is 4.9 gigabytes. It loads into VRAM in one shot and runs at 64 tokens a second. Qwen 3 Next is 20 times larger than that. Llama.cpp does not have a plan B for models that do not fit. The file is too big, the loader refuses, and you get a wall. oLLM ignores the wall. So the question stops being, does the model fit? And becomes, how does anything run at all? oLLM is a Python library built on Hugging Face transformers and PyTorch. It loads transformer layers off your SSD one at a time, runs each one on the GPU, and throws it away before loading the next. The model never fully exists in memory. The attention cache goes to the drive as well, at full 16-bit precision, written out as attention runs and read back when it is needed. Big MLP projection matrices get chunked into passes small enough to fit. Flash attention keeps the full attention matrix from ever materializing. The result is that peak video memory stays under 7.5 gigabytes, no matter how large the model is. That is oLLM, and it is where the tooling gets interesting, because you can see the design in one strange row in that README table. The 20 billion parameter GPT-as model runs slower than the 80 billion parameter Qwen 3 Next. GPT-as loads all its experts onto the GPU. Qwen 3 Next is a mixture of experts model, and oLLM only streams the experts a given token actually routes to. The other experts do not make the trip. Larger model, fewer weights moving per token. Sparsity is doing the same thing here that it does in llama.cpp, just over a different bottleneck. Now, if you have actually tried this, you have probably already run into the number. Half a token a second, maybe 1. And before you file a bug report, here's what that number is. The RTX 3060 Ti reads its own VRAM at 448 gigabytes a second. A fast PCIe 4 NVMe drive reads at about 5. Ratio of roughly 90. Every token has to walk the active layers of the model off wherever they live. So whatever ratio your storage has, your tokens per second inherits it. That 129 times gap against llama.cpp was never really about the code. It is a memory bus against a disk cable showing up as a number you can watch on screen. You can watch it happen in the utilization graph. During decode, the GPU sits mostly idle, waiting for the drive to hand it the next layer. Someone on the Hacker News thread asked the obvious question. If you are bottlenecked on SSD bandwidth, why even use the GPU at that point? A CPU would be just as fast. The author replied that the GPU still does the arithmetic far faster than a CPU once the layer arrives, and that every tier you can pull into the pipeline helps. The bottleneck moved. It did not disappear. The sharpest counterargument in that thread came from someone with an M2 Max and 64 gigabytes of unified memory. Same model class at 4-bit using MLX, 42 tokens a second. Same idea, opposite conclusion. Fit the model into fast memory and you win by 80 times. That is the ceiling oLLM is bumping against, and no flag will move it. And this is where the tooling gets awkward in a different way. oLLM does not give you a lot of knobs. The behavior you want is mostly the default. You point it at a Hugging Face model, you get streaming layer offload, flash attention, chunked projections, and a cache on disk. The configuration surface is small because the design choices are already made, which is useful to understand because it means when something is slow, it is not a misconfiguration. It is the bus. There is a second catch underneath that one. If your SSD is slow, the numbers get worse faster than you expect. A PCIe 3 drive at 3 gigabytes a second instead of 5 cuts tokens per second by another 40%. A SATA SSD is another 3 to 4 times slower than that. The readme numbers assume a fast NVMe drive. If yours is not, the gap widens. And the context fight is separate. Qwen 3, next ships with 131,000 tokens of context. The attention cache at full 16-bit precision grows with every token you generate. At 50,000 tokens of context on an 8 billion parameter model, the cache alone is 52 gigabytes. That cache lives on the drive. A fast NVMe can handle it. An SSD with heavy existing write load, or one nearing the end of its write endurance, is a different situation. The author was asked directly how badly this shortens drive life. His reply, "Good question. Need to research this one." That answer has not been updated. A paper from August 2025 made the broader argument. The title does the work. SSD offloading for mixture of experts weights considered harmful in energy efficiency. Pulling weights off a drive burns more joules than the cheap hardware saves you in dollars. That is a real number, and it belongs in the decision. So, that is the speed half. The context fight is worth finishing. llama.cpp on 8 gigabytes of VRAM with an 8 billion parameter model at 4-bit hits, a ceiling around 32,000 tokens. 2 independent write-ups this spring reach the same number. Push to 64,000 and it probably crashes. oLLM on that same 8 gigabytes runs the same model at 100,000 tokens. Cache on disk, 6.6 gigabytes of VRAM, 69 gigabytes of disk. There is a shape of job where the speed comparison stops working because one side does not finish at all. One enormous document, full precision, 8 gigabytes of video memory, no cloud because the document cannot leave the building. A contract, a regulatory filing, a patient history, a year of log files. Read the whole thing in one local pass. The author says so himself. This is not a chat engine. It is an execution path for large context offline passes. One question left, and it decides whether any of this was worth doing. Is the 16-bit copy still the model that ran the benchmark? Almost every local model you have ever run was quantized. 4-bit takes a weight stored at 16 bits and rounds it down to 4. 16 possible values instead of 65,000. You give up some accuracy and the file gets 4 times smaller. oLLM does not do that. It runs 16-bit weights and keeps the cache at full precision on purpose, because rounding is exactly the thing it is trying to avoid. Which means the model answering your questions is the model that scored the benchmark, not the compressed copy. That is the one place oLLM is not making a trade. The commit count is the last number worth looking at, and it is the one I did not expect. llama.cpp had 5 separate tagged builds in a single 48-hour window. The most recent one landed a few hours before the script was finished. oLLM has had exactly 1 commit in all of 2026. 1 line in the project file, pinning a library version. The last commit that changed how anything behaves was November 29th, 2025. The roadmap the author posted at launch. 100,000 token context on 12 gigabytes. A better cache algorithm for mixture of experts models. None of it shipped. 2,700 stars, and the work stopped. The idea is more interesting than the throughput, and sooner or later somebody will implement it properly in C++. So, set the bar where it belongs. Half a token a second is far too slow for an agent grinding through a codebase unattended. It is fine for reading a 50,000 token filing and getting an answer by morning. Here's how I would actually decide. If you want to talk to a model, install llama.cpp. Quantize to 4-bit, cap your context at 32,000 tokens on 8 gigabytes of VRAM, and stop reading benchmark tables. If the model does not fit, still llama.cpp. Try first, then let memory mapping page from an NVMe drive and make peace with 1 to 2 tokens a second. If you need 100,000 tokens at full precision on 8 gigabytes, and you can wait, oLLM is currently the only thing that does it. That group is small. It is also real, and until llama.cpp puts the attention cache on disk properly, that group is the entire reason this project exists. The thing worth keeping is not the setup instructions. For 2 years, the rule was that VRAM is a wall. The model fits or it does not, and the only fix is a bigger card or a smaller model. oLLM turned that wall into a door. A slow door, one you have to walk through at half a token a second, but a door. 80 billion parameters, 8 gigabytes, answers in real time. Go run it, then tell me your tokens per second and your drive speed. Those 2 numbers together are the whole story. See you in the next one.